I'm Alejandro del Castillo. I work at National Instruments. I'm here presenting National Instruments with Sergey. And today I'm gonna be talking about what are we doing to integrate SALT as the system configuration management engine for our embedded devices, which probably makes us kind of the oddball at this conference, since it's mainly DevOps and cloud people, and I'm an embedded developer, so I don't understand a lot of what you guys say, but the problem is the same. The same problem that you solve when you are provisioning on the cloud is the same problem that we need to solve for embedded devices. So I'm going to cover a bit of background of what is the problem, then go through the thought process when we chose SALT as our solution. Then I'm going to cover some of the challenges that we have using SALT on the embedded domain. Then I'm going to cover how the integration is happening with our platform, and then cover a few takeaways. If you have questions at any time, we are a small crowd, so just ask. So that's NI's mission, a little vague like company missions are. Basically, what we do is that we do hardware that takes measurements from the world, signals, and then we sell the software to process those measurements to either get analytics on what you're measuring or do control loops, that sort of thing. NI has been going for a while. It was founded in '76, and at that point, the business was around GPIB. It's a bus that is used to control instruments. In '86, LabVIEW was created. That's the flagship product that NI is mainly known about. And the idea at that point was that a computer is a pretty powerful instrument. So if you just sell the hardware to convert a computer into an oscilloscope or a DMM, well, you can sell that and then use the processor in your computer to create what we call a virtual instrument. So that was the model for a while. And then around 2000, we went more into the embedded space to create embedded rock controllers that go into wind turbines, as well as very high-end fast controllers, which are modular. So you basically have the controller and then a bunch of slots where you put your instruments, RF, DMMs, oscilloscope, and a bunch of others. So around 2011, these controllers run real-time operating systems. So basically, for those of you who are not familiar with them, are operating systems that are tuned to be deterministic. So basically, the latencies are not unbounded. So that's at the very core of all our embedded offering. And we were using proprietary systems. We were using VxWorks and FireLab. But in 2011, we decided to use Linux. So Linux has what is called the PreemptRT patch. That it's a patch that makes Linux deterministic. And it's really powerful. It transforms spin logs into RT mutexes, as priority inheritance, as high-resolution timers. And this patch actually is an RT collaborative project for the Linux Foundation, where now there's a bunch of companies collaborating to upstream into the main kernel the RT patch. And at the time, I remember there was a quote for Linus Torvalds saying, like, it's crazy if you are trying to make Linux real-time, but like 10 years after, it's many companies are basing their critical systems on it. So being an embedded developer, you may be thinking, what am I doing here? And the thing is, like, the same trend that consumer devices that are affecting consumer devices are affecting civil infrastructure as well. So right now, a lot more things are being connected, and that's what it's called the Internet of Things. It's a loaded term, and then we load it even more by calling it the industrial Internet of Things. But the whole point is that now you have smart grids, power plants, tractors, all sending information to the cloud. And with that, well, there comes system configuration management needs. So we have existing solutions. We have two. The first one is called Measurement and Automation Explorer. The graph is pretty bad, but basically here you have a bunch of targets, and then if you click on each target, you're gonna see things like serial number, network settings, and you can change them here. So it gives you an interface that is proprietary, is push-based, it doesn't have it's agentless, and it's imperative. For more enterprise solutions, we have Insight CM, which it's closer to the model that Salt, Chef, Puppet use, where you have an agent. This is a web page running a server, and then you can see all your targets. And this scales. This is supposed to scale to the thousands. But it's also proprietary and is imperative. So at this point, we didn't have much of a choice because VxWorks and Farlab are single process operating systems. Like the OS is compiled with your application, so you just run a monolithic application that does one thing and only one thing. When we move to Linux RT, then suddenly there's a whole ecosystem that we can start using. So at this point in time, in 2011, suddenly we had the option of not go with this and then have a new solution. So at that point, the question was, should we be developing our own, or should we be leveraging something existing? So the thinking was that the world doesn't need another Ansible, Chef, Puppet. We already have 4 pretty good ones. And we're not experts on system configuration management. And system configuration management is not a core part of our business. We are not a system configuration management company. We deliver value to our clients, providing very good hardware as well as with LabVIEW. System configuration management is a given that clients expect that we're going to give them, but I don't think we're going to innovate there. So following that train of thought, we basically, well, as the title of the presentation suggests, we decided to go with Salt. It also gives us interoperability and the opportunity to leverage all the features that the community is putting in the project, and we contribute back. So why Salt? The main 2 bullet points are the main reasons from my point of view. The event bus, it's awesome. We leverage it. We use it a lot. It's very important for us. The second thing is that our controllers, our clients usually program them with LabVIEW, but also they run their own applications. So they expect an interpreter. Right now we only have Bash. If we put Puppet, then we'll be putting Ruby. And if you get a brand new controller, latest technology with Ruby, well, everyone will be expecting Python. So those were the main 2 reasons, but there were others. This is actually the table that I presented to our leadership with a comparison that we did. There's been tons and tons of these tables. Everyone has their own to compare the 4 main ones. But the point that I want to drive here is that when we chose Salt, we identify holes. The stuff that is on red, we knew that Salt didn't have Saltmaster support on Windows, and we have to run on Windows. It's a requirement. It's big. If 70 megs, Python is. That's too big. We want to be running lower into our deployment curve. For embedded systems, the most commonly used tool to create custom distributions is called OpenWRT Yocto. It's a Linux Foundation project backed by Intel. It's great, and it's a way to basically say, I want my image to have kernel with this version, BCBox, Puppet, everything, and then it bakes everything into an image. Well, it didn't have Salt support. It did have Puppet and Chef support, by the way. And OPackage, it's depackage little cousin. So it's an embedded package manager. And yeah, Puppet and Ansible have support for package. Salt didn't. So we chose Salt and decided to fill those gaps, knowing, okay, we think it's a superior technology. It takes us 70% of the way. It's worth investing to take us, and we do the extra legwork and contribute it back. So now I'm going to be talking about some of the challenges, and I chose a few. I'm pretty sure there are others. Sergey has been working also in a few others that I didn't put here, but these are some of the ones that I chose. As I mentioned, the footprint was at 70 megs, and we're tied to that because we're using OpenEmbedded, and when you say on OpenEmbedded, pull Python, it goes and pull Pythons with a lot of stuff. So the solution was to use a pretty obscure feature of Python that lets you zip all your core libraries into a Python 27.zip, that if you put that on your library folder, the Python binary will try to load that first. So if this is there first, it's going to go there and compress it and use it. Yeah, it's not documented. I just found a few references. And then looking at the code, yeah, that's what it does. So we did that, and then you get on your python.zip file, you get to pick and choose what you want. So then you can drop all the stuff that you don't need, and then you get something a lot smaller. I had to create a patch for the binary because the binary looks for user-lib Python 2.7 ps.py. Yeah, that's bad. os.py. Yeah, I'm dyslexic or something. So the patch basically just makes it look for this file instead. And it's a backport for Python 3. Python 3 does that. So I just applied that to Python 2. And then it worked, and we were down to 37 megs. If any of you guys are interested in more nitty-gritty details, as well as the Python zip recipe, I haven't upstreamed that one, but I can just give it to you. So the second problem that we found is that on real-time systems, so the way that Linux works is that it lets you overcommit memory. So if you have you have 2 gigs of RAM, and then you have an application that says, I want 4 gigs of RAM, the kernel tells you, yep, that's fine. And the way it works is that physical memory is being accounted for, and when it hits a certain threshold that is configurable, the out-of-memory killer kicks in, which is a process that basically goes and kills one of the running processes using some heuristics. So to me, that's one of the weaker points of the Linux kernel. There is work to make it better. Those heuristics are not great. I heard an analogy that was pretty good that says, like, okay, you're in a plane and it's too heavy. You need to, someone has to go, right? So basically there's a raffle, and then the pilot is the one that is chosen, and then he goes out. So the out-of-memory killer is like that. So for embedded system, the thing that is suggested is that you disable it. But the problem with it is that now your process, if it claims a certain amount of virtual memory, is going to be claimed against the physical memory. So Salt spawns a bunch of threads, and we noticed that running, even without connecting, it was at 300 plus megs of virtual memory being allocated, which was worrisome. Our first targets have about 2 gigs of memory, but we plan to go down the deployment curve. So the good news is that those huge memory allocations, I'm not sure it can be seen here, but are mainly made of chunks of 64 megs, and those are chunks that come from libc thread pools. And those thread pools, if you go into your proc maps, are set to private memory. So the way it works is that you have a scratch pile of memory, and then if your thread needs memory, it grabs it from there. The thing is that the kernel has special code to tell you if the memory is set to be private, don't use it against the overcommit limit. So even if we're setting overcommit limit equals to 2, it's fine to have huge virtual memory allocations as long as it comes from thread pools. So Yeah, that was interesting. The other thing that we need to take care of is that it's an absolute requirement for us to have the Salt master running on Windows. So what we did is that Sergey went ahead and checked what was required to basically make it work on Windows. And he identified over a few things, but these are some of the things he identified, like there were problems with IPC, some Unix assumptions. You have to use picklink because of the way processes work. And he got it working. So we upstream it, and now there's Windows support on for the Salt master. So the other thing that we did when we started this project is have as a philosophy that everything that we do, we will upstream. Even if it takes us longer, even if we need to make a more generic solution, we will go and make the generic solution, because on the long run, for a lot of reasons that you guys are probably familiar with, you just want to, it's in your best interest to do that. We also had the problem, we didn't have support for embedded, so there was no package module, and no open embedded Yocto support. So we did the same thing. We went ahead and created the package execution module, and went ahead and created the recipe for Salt on Open Embedded. So now basically everyone that is creating using Open Embedded to create a custom distribution can go ahead and install Salt and use a package. So that's cool. So this is the way our stuff looks like. These are our high-end controllers. They're called PXI. They're based on PCI Express. Compact Rio, these are our smaller raw targets. These are the modules that you just swap, and if you want different type of measurements or signal conditioning. Going down, we have single board Rio and then system on a module. So at some point, there's going to be a cutoff, right? I think it's about a 512 megs. I'm not sure. We're going to need to do some experimentation. The good thing is that Salt has the Salt proxy, so that gives us an out. If we want to use Salt in targets that are too small, we have a pretty good way to solve the problem. And yeah, yesterday I went to the Salt proxy presentation, and yeah, it's great. I think we should be able to use it. So now I'm going to move ahead and talk about how we're integrating it within our product. So LabVIEW, it's a family of products. One member of that family is LabVIEW for comms, for communication. It's used for RF. A lot of people doing like 5G research and that sort of things. So that's the first product that has Salt on the back end. So this is how it looks like. This is the lobby where you have 4 PXI chassis. The way we discover them is that the chassis are announcing via MDNS, which is a broadcast protocol, I think first created by Apple, but then, yeah, and now there's Avahi, which is like a clone, I think, which is the one we use actually. So it doesn't quite work like this on the first release, but we're planning to have an engine that is going to do the announcement. So it's announced, it's there, and then you want to claim it. So how does that happen? So these targets have SSH enabled, and we precede the keys on the master. Then via SSH, we put the keys on the Minion, we restart the Minion, and you're done. I just took this verbatim from SaltStack's webpage. There's a precede Minion keys great tutorial. So this is the way it works. You go ahead and connect to a target. It can be local, or if it's not in the same subnet, you just need to put the domain or IP. You put your SSH keys, then you wait, and now it's here. So at this point, Salt is all in the background, but basically now your target is connected to a master. So after it's registered, this is just a sneak peek, but we have the concept of a system diagram where here you will see your different targets, your chassis, and you can connect them Ethernet, USB, and then you open this and you program inside using LabVIEW, and it's kind of a way to see your whole system, right? As part of that, it's also the way to configure your system. So here, it doesn't show really well, but here you have your network settings. And the way it works is that they are being read from MongoDB. So we're keeping all the grains information on MongoDB. And we show them that here on the system diagram. If you then go ahead and click on Configure Network Settings, you get to change your settings, and that ends up being a Salt execution module call. So at that point, the network settings are applied, and it's all transparent. The thing is that right here, the settings are being read from MongoDB, so your settings need to be updated on MongoDB. The way we do that is that we have a beacon that is checking. It uses the IPDB Python module. It's great. I didn't know it existed, but basically, it gives you an object with the state of your network settings. So then the beacon emits again, and you check if your network settings change. And if it change, then you create an event. So that's how we do it. And then on the master, we have a reactor that when that event is registered, it calls a runner, which does get grains. So that's kind of how we work on it. And the network settings beacon, we went ahead and upstreamed that too and make it generic, so you can choose like which things, changes in which things are gonna trigger an event. Yeah. Following the same paradigm, there's a way here to change datetime. You open a dialog, you change your datetime, and in the back end, that's gonna be an execution module call, basically. Resource monitoring, we also have a way to have status where you can show you memory usage, CPU usage, etc. At this point, we are using kind of the legacy technology that we had before. The idea will be that this will be doing it in a more salty way. Probably whenever you open the box, maybe at that point you will enable a beacon, and then if you close the box, you may disable it unless you want to have alarming or, I don't know, something like that. Software installation. So how am I doing with time? Oh, pretty good. Software installation. With software installation, we're planning to do the same thing. Right now, it's not implemented yet, but the whole idea is that on MongoDB, we're going to have all the software installed on the targets. So then, from LabVIEW, we can give you a UI or what's available. So you can, basically it's gonna be a front end to the package state module. You choose what you wanna install, the state gets applied, you again get all the software, all that is plugged into MongoDB again. And what that let us do is that if we know exactly all the software that is installed, then we can replicate it very easily. And that's very important for us, because if you just grab that state and apply it to 1,000 targets, in the embedded space, you really want to know exactly which versions of everything is being installed. So if you have that on MongoDB, you can do it. So we're still playing with it. It's not implemented yet, but we will in future versions of the product. So to finalize, I shamelessly stole this slide from Joseph Hall from one of his presentations. I think here at SaltConf, where he was saying, okay, these are all the things that I think should be salted, which are all embedded things. So I see what we're doing. Like we're helping this use case. For example, OpenWRT. OpenWRT, for those of you who are not familiar with it, it's a Linux distribution for routers that Linux is created. They infringe GPL. So I think the free software, one of the foundations that go after GPL infringements, sue them, and they did the right thing and opened the whole thing, and it became the most popular distribution for routers. It runs a package and is built using Open Embedded. So now you can get Salt on them. Some of the key takeaways from the whole experience. We're feeling good about the choice that we make. We are releasing the first product that is integrating Salt. We're not all the way there, but we are close, and we now have a team of people that are making it go more native to make things more salty. We're very glad that we engaged early. So early we were on the mailing list, on the meetups with you guys. And IRC, you know, we participated on a hackathon too. And the other key thing that I'm really glad that we did is that when we're looking at the solutions, we said, okay, we're not looking for a solution that is going to do everything that we want. We're going to look for the best solution, and we're going to implement the rest so it will do exactly what we want. So moving forward, that's still our mentality. Sergey here has contributed a lot to very core parts of Salt to make it work for our embedded use case. I have contributed to, and moving forward, we plan to onboard more people. And by doing that, I think we're going to be making Salt in embedded more successful. So with that, that's my presentation. I'm not sure if you guys have any questions. Yes? Oh, sorry.
So is the master something like the client would install on their Windows operating system? Is that why you have the Windows?
Yes, so LabVIEW, our flagship product, it mainly runs on Windows. So when we install LabVIEW, now we are installing a Salt master. So the way we're going to do it is that you install it and it's transparent to you. But we will say that this is running a Salt master. So if someone wants to manage their systems differently, they can just go ahead and do it. It's open, so they can do it the same way that they can mess with their embedded targets because they are Linux RT. Yes?
About the same question.
Oh, okay.
Yeah, I was just curious about that because it seems like you got a master on Linux, maybe pretty well UI.
Yeah, so you can think of this as it's a editor for a programming language. The programming language is LabVIEW, so is the installer is like the installer that you will expect from Visual Studio, right? It's only on Windows. You won't be expecting to have another machine that is actually running a master. We see it as two different use cases, like the guy that has a couple of instruments next to his desk, and then the power plant development all around the world that needs a dedicated server that is going to be, having hundreds, if not thousands, of minions. The key thing is that we decided to go with Salt for both use cases. Any other questions? Yes?
Last 2 years, we've seen vulnerabilities in industrial pre-shared keys that are factories. When the client installs the master key, I'm assuming that it generates a new master key at that point, and that gets populated down to devices. Is that true?
So the question, let me rephrase what you just said, is that are we rotating the key on the master? Yes, whenever you register it. So whenever you by default, no. Out of the manufacturing, there's none of that. But no, at the registration process, that's when that exchange happens, and it happens over SSH. And at that point, we ask for SSH credentials, and hopefully that's not compromised. If not, yeah.
So I think to clarify, the salt master's key itself is also generated at install time, just like a normal salt master.
Yes, yes, that's true. Any other questions? Okay, well, thank you. That's it for SaltConf, I guess.